So we'll see an application of bare category theorem, but also an answer to a question or an issue which was there. Are there spaces that are regular but not normal? We saw that if they're second countable, then regular implies normal. And our important case of Urison metrization theorem, we needed second countable anyway. But this is an interesting space to note, and it also, as I said, illustrates bare category theorem. So we'll take as a set points xy such that y is greater than or equal to 0. And we'll take a basic open sets, two kinds as in the picture there. So ball of radius xr contained in, well, let me be a little bit precise, a ball around a point xy of radius r such that y is positive, so we are in a positive direction, and we also have the r is less than, well, it should hit y. Well, I think equal to y will also be fine. R is less than or equal to y, so that the ball does not go below the x-axis. Okay, so these are blue balls. It could be just touching here as well. So this kind, and so there are two kinds. And I'm not going to write the equation. Oh, I might as well. So suppose this is the point x0, and this is going to be the radius r. So the center is then going to be x and r. Okay, so for r greater than 0 and x in r, so ball of radius x comma, a ball at centered around x comma r of radius r, but we also include this point union the single point x0. So this is kind of like a, well, not compactification, it doesn't make it compact, but adding a boundary. But if we approach in different directions to different points in the boundary, they're sort of completely far apart. So it's not as if we treat 2 points. If 2 points are very close to the boundary, we do not treat them as being close to each other unless, I mean, yeah. So if they're close enough to the boundary, they have to be very, very close compared to how close they are to the boundary. Well, this you have already in things like hyperbolic space, but this is an extreme case. Yeah, so where you just have it in particular. R has with subspace topology. So if I look at the subspace topology, well, it's easy to see is discrete. That's because as R intersection this set is the single point. So we have a single point. So the only thing to note is that this is actually a basis. It's not hard to see because if I have two balls centered here, their intersection is the smaller one. And if you have two balls disjoint, so if I had a second ball, which I will also draw dotted, if I had a second ball, if I had a circle here, second ball touching like this, well, you can see that if their points are distinct, then they don't intersect. They don't intersect at infinity, that is at r. Instead, they intersect at some interior point, and if I took an interior point in intersection, I can put a blue circle inside it. Okay, and that is open. So intersection of open sets is a union of basic open sets is a union of basic open sets. So this indeed does form a basis. So given basic open sets and a point in the intersection, there is a basic open set contained in the intersection. So this is an interesting space. R with a discrete space is so this is Hausdorff, and in fact this is regular. So proposition X is regular. Okay, so we use the fact, well, of course we know that we have a metric itself in R2. So if I have a closed set, if I have a point in R2, so let A be closed. Let's pick A and X and closed. And P is a point in capital X minus A. So it's a point away from this. We have to separate them. If P is in R squared, just then as in R squared, as in metric spaces, we can separate A and X, A and P. By which I mean there's an open set containing A and an open set containing P, and these two are disjoint. Namely, we have a certain distance between this closed set. Just using the Euclidean distance, the funny behavior at infinity doesn't matter. Okay, so that separates these two. Now, if P is in R, of course, this is a little more complicated. But to start with, we note that there is a, so as A is closed, so suppose P is in R. Okay, as A is closed, there is a basic open set or neighborhood open set containing P disjoint from E. Okay, so we have some point here, and then we have some basic open set, which again I will draw in purple like this, which is disjoint from E. And so whatever A is, it doesn't intersect this set. So as far as points in R are concerned, okay, so it's easy. So it doesn't intersect this set. So it means, okay, let's take a smaller basic open set inside this, so that there's some distance here in the interior at least. I mean, interior, I mean away from R. Okay. So now for any point here in A, we find a basic neighborhood which is away from this open set, and then we take the appropriate union. So what we have is this, and now what we note is that for any, so we have two cases now. If for any A in A, let me say, or I have my point P, so let's say Q in A. If we have two cases, so if Q in R, or let me just note the common point, either way, we can find a disk centered at Q, if Q. So the open disk and open centered at Q, and let me say an open okay. There is a basic open set. Let's give this a number name, say U prime, containing E, and let U containing U prime be smaller. So U bar is also contained in U prime. So we found a basic open set. We find an even mode which is disjoint from A. So now given any point in A, this is simply the metric space argument. We can find a ball. We can find a disk centered at Q and open if the point Q is in R2 minus, I'll call it X minus R. So we have taken this disk and we have taken a smaller disk. Given any point here, we can find a ball. Well, this one was very close, but whatever the point is, we can find a ball centered around this. Okay, so we call this disk centered at X, disk, it's an open disk, centered at X, which is disjoint from the inner disk. Okay, and if X belong to K and touching and adjacent, or rather, so we can find this disk which is open in this case, or we can find a disk which is touching R at Q, disjoint. So touching R at Q, I should clarify. So this is if Q in R. disjoint from U in both cases. Okay, and now we'll take V is union over all x in A of dx. It seems like nothing much had to be done, and indeed nothing much had to be done, because this is just an extension of the fact that metric spaces are regular. Point being, we had only one point at most, and the only difficult case was when that point was in R. But even then we had a disk around it, and we could take a smaller disk around it. And when we have one disk, two disks that are incident, and one disk this way and one disk this way, any point outside the outer disk has a definite distance to the inner disk unless it's actually lying on the real axis. And even then, it has a definite distance to this disk. I mean, if it's actually lying on the real axis, it still has a definite distance to the inner disk, just by simple geometry. And so we take a small enough disk around a point like this, or an adjacent disk, which becomes disjoint. So either way, we have seen that this is regular. The non-normal case is a little bit deeper. As I said, it uses the bare category theorem. So here's the thing. Let me just say theorem. X is not normal. Now, which sets do we not separate? You would guess that they are closed subsets of R. And remember, every closed subset of R, every subset of R is closed because R has the discrete topology. So let A equals R minus, I should clarify that, and B equals Q. These are closed not only in R, but these are closed in X. As R has discrete topology, first of all, so they're closed in R, and R is closed in X. Why is R closed in X? For the usual reason. If I have any point that's not in R, there's a disk which is disjoint from R. So R is closed in X exactly for the same reason it's closed in R2. So we have these. Okay, so claim is that we cannot separate these. Okay, so let A contain in U, B contain in V, be open. Okay, so we claim they cannot be disjoint. Okay. So what does this mean in terms of U? So we claim U intersection V is non-empty. What does this mean in terms of what is this set U? Well, it contains every irrational point, so it contains a disk around each irrational point. Okay, so for all x in R minus Q, what we have is that the ball around x of radius okay, so there exists some number R of x greater than 0, such that if I look at the ball around x of radius R of x, this is contained in U. Okay, so now, so we have R of x positive number. So now we define Zn. This is a typical argument in bare category theorem. The rational numbers are already countable. For each irrational, we'll filter. We'll look at those irrational numbers which have a large enough R. And large enough meaning for each n, we'll look at those x in R minus Q such that we have R of x is greater than 1 over n. I could take greater than or equal to also, that's fine here. Okay, so then what we know is R equals Q union of oh, I put an equal to by mistake. Now suddenly we are looking at R with its usual topology. Okay, so union n belongs to n of Zn. Okay, so now we're just going to be defining these sets. So now we have to get a contradiction from here. So by Bayes' theorem, so we'll consider R with its usual topology. Bayes' theorem for R with the usual topology. not the discrete one coming from X, which will tell us nothing. So not Q is countable. And points are nowhere dense. Okay, so we cannot have Zn nowhere dense. Dense for all n. That is, there exists n in n, natural number, such that if I look at the complement of the closure of Zn, R minus Zn bar is not dense. Okay, so being not dense in R means there is a point and an open neighborhood, or there's just an open set, hence an open interval, which does not intersect this. Okay, hence there is an interval A comma B contained in Zn bar. But now note the crucial thing, we have a fixed n, so every irrational point here has a ball of a fixed size around it. Okay, they'll overlap each other, that's not a problem, but they're in U. Okay, and now we can contradict. So it follows that if I take some x in the rational numbers intersection AB. Okay, this picture has become too small, so I'll blow it up. I was trying to keep things small because they're supposed to be, but that makes things not very visible. So I have a whole interval, and given any point in this interval, there is a definite sized ball, size 1 over n, given any irrational point, which is contained in the set U. Now if I take any rational point here, and I take any ball around it, this will hit a ball of radius 1 over n around the close enough irrational point. Okay, so it follows that if x belongs to Q x belongs to Q intersection AB, okay, then any basic neighborhood of x intersects V. Okay, so again this picture is, let's give myself a bit of space. So I have a point x and I take a basic neighborhood which is a disk. Okay, this disk could be tiny, but however tiny it is, I have a fixed size 1 over n, which again might be tiny. Okay, so if I had another point here which was irrational, y, which is sufficiently far away they won't intersect. But we know that an entire interval has things of this same size 1 over n, and if it's close enough they do intersect. You can calculate the number of these. So it follows that if I take any basic neighborhood of x, it intersects this, hence U intersection V is non-empty, as U must contain some such basic neighborhood. Some such basic neighborhood. So some basic neighborhood of x. Okay, hence if I have any open sets containing R minus Q and Q, they must intersect each other. So there are other applications of bare category theorem, famous ones, like you can't have functions that are continuous at exactly the rational points. They follow the same spirit, that you filter things, and the filtration, if you have a filtration, countable filtration of irrational numbers, one of them must be everything. I mean, so we can't have one of them must be dense somewhere at least. They can't all be nowhere dense. This will give you a uniform control, and which will lead to various contradictions.